a set of n random variables. These set of n random variables are joint. So the joint probability is jointly Gaussian. We indicate in this way. So we say that this set of n random variables is behaving as normal, so it's Gaussian, with a certain mean value, which is mu x, and with a certain covariance matrix, which is a CXS. Rather than, I mean, this is the compact way, okay? So if when I write it this way, I might also say that the joint probability density function, okay? Remember, joint is a multi-dimensional function, which is n variables plus the value, so it's n plus 1, so it's impossible. Unless, we don't do like with two variables, okay? So, but if it is more than two, it's complicated to have a picture of that. So anyway, so if you consider these, the joint probability, we say this is one is g of x means it's Gaussian on the variable x, and then mu x and cxx is mean and covariance. Okay, so mean, is the first moment, covariance is the second central moment. And the representation is the following, where the argument is quadratic form. The mean and the covariance is defined here. Now just a mnemonic rule, okay? The mean is a mean for every entry. The covariance takes the first vector, takes the second vector, okay? So makes the outer product, is called outer product, okay? We have the first vector, which is the vector, second is a row vector, okay? And so in this way, I generate a matrix. To illustrate, I made the example with the n equal to. Now, we have seen that there are many linear transformations, okay, in problems, such as when I have a linear regression model, or I'm filtering, or some problems like a frequency model, or any other. So if I'm lucky, I can describe the problem as a linear. Now in that case, so consider a case where, just to exemplify again, consider the case where I have a system okay, which is filtered by the filter G, and so what I measure is X. Okay? And so what we did specifically, we said that, for instance, if U is the input, okay, and then I can describe X as, it's G vector convolve U vector. This is a notation, compact notation. I can also swap the value, so it is U vector convolve G vector. But rather than writing this way, I can write in a matrix form. And the matrix form is G multiplied with the vector U. And G is a convolution matrix. Okay. Or, which is the same because of that property, is U as a convolution matrix times G. Okay? So this is what we saw. Now let's consider the case where U is random. Okay? Perhaps U can be associated to a random process. So if U is random, you need a set of random values. Okay? This is simple, like the music, like the voice. Then my goal is that I want to manipulate my data such that I want to find the property of X. Okay? So let's assume that, for instance, U is random with a mean that is mu U and the covariance that is U CU. Okay? So let me just so that the example remains on the slides and so the write it. Okay? So we are looking at the example where we are. I'm just copying, okay, you're not thinking. So U, G, and then X, okay? And I can write that is a set of values as U vector, so U matrix, convolution matrix times G, or which is equal to G convolution matrix times G. Okay. Now, let's make even more. So let's assume now that U is random. Is a set of random values. Okay, so this set of random variables is a block of n samples. So which means, just to exemplify, I'm listening to music, blah blah blah. Okay, then I slice one interval n of data. Now we assume that this is stationary. We will refresh a little bit the concept, but intuitively, stationary means that the property is independent of time. So whatever I cut, the property remains the same. Okay. So this is a set of values that the random values that I'm considering. So this U vector, remember U is a vector n. Okay. So this U vector, okay, is, we can assume it's normal with a mean that is nu u and the covariance that is c nu u. Okay. So that means that the probability density function P u, okay, is Gaussian. Okay, G now don't confuse with the other G. Okay, so I don't write this way, otherwise you get confused. Okay, let's stay in this way for now. Yeah? Now, so let me ask you a couple of comments on that before entering into what I want to discuss. So if the random values, okay, so these are the random values, just to exemplify, I don't know, this is, okay, this is a realization. Realization means, it's just one sample extracted out of many, okay, and this is the n, I don't know, 1,000, okay, just to say a number, 1,000 samples. So I have these 1,000 samples. Then I want to say that what is the property in a mean? So, in this case, for instance, if this one is the time axis, and if the random variables is fluctuating around 0, so I can say that in this case, mu u is, it's 0. Okay. 0 means it's a vector of 0. Okay. So this one is n times 1, and this is n times 1, which is equal to 0. 0, 0, 0. Okay? Now, what about the covariance? Okay. Now, let's assume that the C, U, U. Okay. We make two models. Okay. What about if C, U, U is equal to, so it contains just the term along the diagonal and nothing else. It's different from 0 along the diagonal and not outside. So this means that, CUU along the diagonal, this entry, okay, so the CUU with a label 1, 1, okay, which is the covariance matrix entry at the position 1, 1, okay, corresponds, let me go back, okay, I read with you, okay, corresponds to the expectation of the variable minus the mean, which is the variance. Okay, so that entry along the diagonal, I read the variance. So along the diagonal, I read the variance. So this means that the entry along the diagonal here, okay, is a sigma u1 square, sigma u2 square, blah 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 until I have a sigma square un. Okay. So along the diagonal, I read the variances of n entries. Okay? So, what about if those values are all the same, and I say that all these values, so all of them are 0. Okay? So what kind of, random variables are these? Now, think about it. So I have a random set, which is taken by the sigma. Okay? And CU1 square is the variance of the first sample. Okay? And let's say that the first sample is 0 mean, so it's fluctuating around here. So that means, I'm trying to illustrate it. That means that I take this sample, and this one is, the deviation that is equal to sigma u1. Okay? Then, I don't know, I take the second one, second sample. Okay, this is sample number 2, so it's enlarging. And then, this one has a variance that is sigma u2, and so forth. Okay? So now, let's make a few cases. What about, as I said, if sigma u1 is equal to sigma u2 is equal to sigma un. Let's make it with a square. What can I say? Now, this is a set of random variables. Now, since there is no off-diagonal terms, the random variables are Gaussian and they are uncorrelated. Okay? Now, that means that the meaning for that means that the expectation of ui minus mu ui multiplied by uj minus mu uj, where I choose two arbitrary values, ui, I and j, okay? This one is equal to 0 for any I different from j. And it is equal to sigma square ui when I is equal to j. Okay? So this is another way of writing this condition. Now, what can I say about this process? This set of random variables. Actually, it's a process that we will put in a formal way a little bit later during the semester. Okay? So, what can I say about this? I can say that this set of random variables, they are all the same. They are not correlating each other. So since the samples are not correlated and it's Gaussian, they are statistically independent. Because for the Gaussian case, uncorrelation and statistical independence are the same because of the property that we discussed last time.
Sorry, are the conditions switched? Isn't it 0 or I equal to j?
Oh. This one, any value here is I different from j. This is I equal j. Okay? So it's, because that is a matrix. Huh? So I have a matrix which is 1, 1, 1, 2, 1, 3, blah, blah, blah. This is 2, 1, 2, 2. So these are all those with I equal j. Okay? And these are all where I equal differ from j. Okay, you see 1, 2, 1, 3, 2, 3, blah, blah. Okay? So now about that, okay? So what can I say? I can conclude by noticing that ui samples are statistically independent. Okay. So they are statistically independent and uncorrelated. Okay. This is for the property for Gaussians. Now, this is a special case. So what can I say? What do I imagine? I imagine, okay, so I take a signal and I see, perturbation. I take a signal, I see a perturbation. I take a signal, I see a perturbation. So that means that if they are all the same, there is no correlation between one sample and the other. Okay? And then, let me say, the standard deviation are similar. The same. Okay? So that means that this is the case of the so-called wide Gaussian process. Okay. Why? Because they're not correlated. Gaussian because it's Gaussian. Okay. So this is the condition given using matrices. Okay. Now, so let's continue that. Okay, so let's consider the case where u is a random variable, okay, so which is taken some way. I want to calculate what is the probability density function. What is the probability density function of x? So my goal is to answer this question. Okay, given that u is normal with a certain mean and with a certain covariance, what's the properties of x equal g convolution matrix kind of? Okay, so this is, the question that I'm trying to address. Okay, this is the question I need to address. Okay, so this kind of experiment. And remember, just I want we're all clear. Okay, this is the convolution matrix, as well as the convolution matrix. So how can I calculate that? So this problem, is called linear transformation for any random vector. That's a linear transformation because I take the vector u and it's transforming into a vector x. So that is a linear transformation. So let's look at the property in general. Okay? So this is the motivation. Now let's look at the property in a general case. Is it clear? Okay. Now the property is reframed. Now it's not the same notation. No, it's not u, x, okay. So remember, all over the semester, I split. And it's not mine, it's because we need to gain the maturity to decouple the way you represent the problem from the problem itself. So the formula you use to represent the problem from the problem itself. The problem is, what is the transformation of the random Gaussian vectors? Okay, now, in this set, the random vector is u, and x is the output. This is a linear transformation, okay? So that's the case. So now, I'm just considering this problem. Then, my goal is, what is the random property of y, assuming that x is the Gaussian vector, and a and b are arbitrary transformations. Okay? Now I can prove that the y is Gaussian as well. Because we know from other courses that any linear transformation of Gaussians remains preserve the Gaussianity. So every linear transformation of Gaussians is Gaussian. Okay? So things about, this comes from the property of Gaussians. Now, what I need to know is, since I know that if x is Gaussian, then y is Gaussian, I need to know what is the mean value of y and what is the covariance of y. So remember, the beauty of Gaussians, you don't appreciate it now, but at the end you will appreciate as a crazy. So the beauty of Gaussian is that it is fully determined by two quantities, the mean and covariance. So, whatever is the complex behavior and the complex environment, but if you have Gaussians, you have the mean and covariance, you're done. You have everything. If it is, if it is a non-Gaussian distributions, then it's a real trouble. Sometimes, you try to reduce the non-Gaussian distribution into a Gaussian one because Gaussian is so convenient. Okay? And we will see in a while. So these are only the two. Let's see. This is the two set of to establish, okay? Now, how to get the mean? You know, the easy way to compute the mean is very easy, by the definition. Okay, so I use the definition here. I compute the mean of y by applying the expectation to y. Okay, as simple as that. Now, I need to remember that my expectation is computed with respect to x, because the only random variable is x. Okay, so warning. Recall that the random variable is x. Okay, never forget. So that means that A and B are deterministic. It's like in the previous example, is the filtering matrix. Okay, so that filtering matrix we assume is known. So then I apply the expectation. You know, the expectation is invariant for linear transformation. Then if I apply the expectation here, you know, what I need to do is I need to apply the expectation of ax plus b. But since the expectation is with respect to x, the only random term is x. So the expectation does not apply on b, does not apply on a. And this gives the formula which is indicated here. So when I apply the expectation now with respect to x on x, that is a mean. So the formula, the outcome formula is that, you know, the mean out is the mean in mu x multiplied by the transformation a plus b. Okay? So, you know, CYY. What is a CYY? I apply the definition as well. So I apply definition, then, you know, I simply need, okay, this is number 2. So what I need to do is, I need to apply the expectation on y. What is y? Y is ax plus b multiplied by y transpose. Okay, y transpose is x transpose a transpose plus b transpose minus minus mu x transpose. Okay, then I continue on that. So I multiply all the terms. So, you know, I have expectation with respect to x of 1 of, you know, ax, x transpose, a transpose, then I have minus, I have a plus, sorry, I have ax b transpose plus b x transpose a transpose, and then I have a plus b transpose. Okay? Minus blah blah blah, which is mu x transpose. Then I continue on that, and then I apply the expectation where I needed to compute the expectation. So I have the expectation of, now I finish the room, but so expectation of A, then I have expectation of x transpose, A transpose. Plus, now I need to apply the expectation. When I apply the expectation to the second term, the only random part is x. So when I calculate the expectation on x, is the mean. So it's plus a mu x b transpose. And similar to the other, it is b mu x transpose a transpose. And then it is plus b transpose. Minus mu x transpose. Okay. Then you use the definition of the covariance of x, and you see that, you know, it's there is a coincidence. So at the end of the story, you know, what comes out, okay, the finish of the story, what comes out is that covariance of y is equal to the covariance of x multiplied by a and a transpose. So it depends on the correlation properties the entry of x. Now, we take this outcome, okay, we apply to our formula. So we go back to our problem, okay, and in our problem, we remember we have the problem of filtering, okay, so we go back on filtering. Now that we learn our property, we go back to filtering. Now the filtering, switch the slide. The filtering, just to recall you, was this one, okay? So then, you know, we have x equal g multiply u. Okay. Then, you know, I mean, this g is the linear transformation of u. Okay? Now, what I can say that this one is Gaussian, so it's normal distributed with a certain mean and with a certain covariance. So the mean of y, mean of x, okay, is equal to g, the mean of u. So the mean of the output is the mean of the input linearly transformed by g. Remember, g is a convolution matrix. Okay? So just, you know, g is a linear transformation of u that, I mean, if I can figure out, is a matrix with all the entries. Okay? Which is, you know, the behavior of a convolution matrix. Okay? So now this is for g, and then, you know, it's the mean is composed in this way. Now, if mu u equals 0, then mu x is equal to g multiplied by 0, which is 0. Okay? So if I have a 0 mean, I get 0. Okay? If means that this is a special case. So in, I don't know, in yellow is the general property. Now, let's consider CXX, covariance out. The covariance out, you know, is, I go back to my formula, okay? And so my formula says, the covariance out is transformation, covariance in, transformation, transpose, okay? So I apply now this formula. So the covariance out is transformation, covariance CUU, transformation, transpose, which is the filtering. Our transformation is the filtering. So if CUU is equal to diagonal okay, so if it is diagonal, the random variables are statistically independent. I cannot say it's a y, because when I say y, you know, there should be every entry, every variance should be the same. Okay, so it's not y. So if it is this case, then, you know, my g, so my c sense, okay, is g, these diagonal g transpose. But, you know, if again CUU is equal to sigma square identity. Now in this case, all variances are the same. This is the case of, you know, white Gaussian variable. Okay. Then, if it is the case, CXX is equal to G transpose multiplied by sigma square U. Okay. Now, I want to elaborate it more on that, okay? Because, I mean, perhaps you are used on the time signals, but I want to do this one in these matrix signals, okay? Because these matrix signals have the capability to manipulate a block of data. This block of data can be time samples. But you know, this block of data can be a vector of data acquired by a set of sensors, different sensors, like an array of sensors, like a set of antennas, okay, and whatever. So you know, this is more general than just the processing the signal in time, because I don't give a name to you. Now, as I said, you know, I want to make a step forward. I want to make two comments. Actually, this will be an exercise, but I'm going to make two comments now that is in front of me. Comment number one. Let me say remark. Consider the case where, for instance, I have a U, which is filtered by G, and I have, you know, and my X superimpose a noise W. Okay? So this is the filtering with noise. W is another random process. So let's make it this way, you know, my X vector, remember, is n and 1. Okay? Oh, by the way, let's give all the dimensional after. Is obtained by G multiplied by U plus W. Okay? So this one, you know, is modeling, typically, is modeling the additive noise or any impairment. Okay, any which is summing up of the data. Okay, so now let's assume, you know, where the data, this one is n time 1. Okay, so I have a block of n data. And my filtering, so this block is n, my filtering is k, and the output, okay, is n plus k minus 1 time n. Okay, so it's a matrix like that. So the output here, x, is n plus k minus 1 time 1. Okay, and so the vector w is n plus k minus 1 time 1. Okay, so just to give a dimension. So now, you know, this was a remark number 1. So if I am in this case, so let's now make the example. Assume that, as I said, you know, so U, let me write lower. Let's make the assumption here. U is normal with a mean mu, and with a covariance mu. Let's say that W is a normal in itself. Okay? And there's a mean that is mu W, and there's a covariance that is CWW. Okay? So let's make the assumption that U and W are statistical independent. Typically, U is the input of the system, W is the noise, you know, thermal noise or similar, they have nothing to do. Okay, so they are statistically independent. So if we are in this case, you know, my goal is to establish what is the property of X. Okay? So the property of X, you know, so I mean, when I write X, I say X is equal to is random, so it's behaving as normal with a mean mu X with a covariance Xx. Now, what is the mean? Now, the mean mu X is equal to, we have seen before, so it is G time the mean of U, and then there is W, plus the mean of W. Because, you know, I have a sum of random process. So if I make the expectation of the sum, and that, you know, is the sum of the expectation. So this is the simple property I'm using. So if I make the expectation of g x plus w. Now, when I make the expectation here, is the expectation with respect to x and w. Jointly. So when I take this expectation, you know, this is equal to g, then I have the expectation of, with respect to x, of x and w, plus the expectation with respect to x and w of w. Okay? But you know, since when I make the expectation of x and w of x, the dependency of w does not exist. So, you know, just let me sketch here so that you remember once forever, okay? When I write it this way, you know, that now this means that I need to compute, to integrate with respect to x and with respect to w of x, then I have the probability density function of x. They are in the statistical independent, huh? And then I have the probability density function of w. dw dx. Okay? Now, but this one does not depend on x. So I can rewrite this as integral with respect to w of p w dw, integrate with respect to x of x p x dx. Okay, this one is the mean. This is the expectation with respect to the x of x. This one, what is that? 1. Perfect. Okay? So technically, I should write, I'm not writing, so I do once, then I'm not going to do forever. Okay? So, but you know, technically, I should write this one as it is g expectation of x, which is the mean of x, plus expectation of w with respect to w. Okay? So that's the reason why it comes out that way. Is it clear? Yes. Okay? There is no magician here. Huh? As I said, you know, I'm setting the background so that our discussion will be smooth as possible for the next. So that means again, you know, this is the general property, number 1. The general property number 2 is that the CXX, the output, is, we know that it is G, CUU, G transpose, plus, now, you know, if I need to calculate the covariance of the sum of two independent variables, the covariance is the sum of the covariances. And so that's the case. So it is C. And that's the second other properties. That will be very useful. Okay? So because when we say the power of the covariance of the sum of random variables is the sum of the variances. Okay? That's the same. So this is remark number 1. Now, by the way, you know, these are properties, let me say, commonly used properties. Okay? So please revise. When you are at home, please look at that. Okay? So fix in the memory. There is no formula to remember. There are only simple rules. Now the second comment, which is a little bit more tricky. Remark number 2. Now this one is a little bit more involved. Let's consider the case where u is y. Okay? So let's make the assumption that CUU is equal to sigma squared u multiplied by identity. Okay. So which means u is, let me say, white noise. Okay? Now I want to know what is CXX. What is the meaning of CXX? Can you read something? Now we know from the process that if I have a white process which is filtered, the output is the convolution of the filtered variable. Okay? We know that. In case you are not familiar with that, we will look at that later. But I want to capture the interest of those that, they are familiar with this group. And perhaps they say, where is this? Okay, so let me show you. Now, let's go here. So I take the second formula, this one, or I take the second one, which is the general, okay, which is this, okay, and I go and analyze this formula. Let's go together. No, so CXX in this case is CXX, so it is G, so it is, C square U multiplied by G and G transpose. Okay. Now, what I want to analyze is these G and G transpose. Okay. Now, before analyzing, let me write it. So let me write G. So if I go back, okay, my G formula is taking all the values and distribute along the column. Where is it? Which chapter is that? So that I think it was chapter 5. Yeah. Yes. So this is the periodic. This one. Okay. So I take this G, this one. Okay. So let me really crop it. So I take it and crop it. The beauty of this system. Okay, I have this one multiplying by itself, okay, transpose. So this is this one, and this is this one, but it is transpose. Okay, so let's see together. So I have G1, G0, G1. Let me copy the other because I don't want to waste too much time. So make a transpose means take the column and put in row. So G0, G1, G, and minus 1. Then the second one, okay, so I take this one and I flip it. The second one, I flip it. Okay, so it is 0, G0, G1, and so forth. Now, let's see the meaning. Now, let's see if I can manage to show it. Now, when I multiply 1 by 1, what I get is that in the first entry, the output is the CXX. So what is in the first position? The first position there is G0 multiplied by G0 plus 0 times 0 plus 0 times 0. So is G0 squared. So in the first position, there is G0 squared. Now, what is it, for instance, in the position here? In the second position. Now, in the second position, there is, it's a G1 multiplying G1 plus G0 multiplied by G0. So in the second position, there is G0 squared plus G1 squared. And so forth. So in the first entry of the matrix, I have G0 squared. Second one is G0 squared plus G1 squared. In the third one, there is G0 squared, G1 squared, G2 squared, blah, 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 okay? So, what's happening in the matrix is, let me sketch it. If you imagine that I do by the color map, do you remember we used the MATLAB, as a calculator, okay? So if I draw the big matrix, okay? So what's happened here, that, the function is, along the diagonal, is growing up, gap to that, and then reducing. So it's growing, constant, reducing, okay? So it's growing until where? Until the position where, I'm summing all. So here I have G0 squared. Here I have G0 squared plus G1 squared. Here I have G0 squared plus G1 squared plus G2 squared. Blah, blah, blah. Until I reach this point. Here I have G0 squared plus blah, blah, blah plus Gn minus 1 squared. Okay, so there is no more. So all the entries here are the same. Then they start to decrease. Now this phenomenon, is the edge effect due to the truncation of the data, because my data is limited to 10. Okay? So you can measure it, you can see it by yourself. Now, what is the entry? For instance, the first one here, the first one in this position, or the second. So the first one there is, now the first here, let me write in different color. Then here, it is G0 times G1. Now, if I make the same in the third position, okay, in the third position, I have G0 times G2. Now, what I read here is the product between G0 and all the other entries. Now, if I make the same exercise, and rather than computing and stripping this part, and start computing here, what I noticed that all the off-diagonal entry are the same. So if strip means, I don't consider this part, and I look at the center of the matrix, I can see that all the entries are the same. And what are the entries? You can try yourself. The entry here, okay, no, that's right. So the entry here, it is the sum of sum for m equals 0 to capital M minus 1 of G of n minus k. And k is the index of the diagonal. So this is for k equals 0, and it's a power. This one is for k equals 1, this is the off diagonal 1, and so forth. So this is nothing else than a cross correlation between the two, impulse response of the filter. So this matrix G transpose contains internally the correlation between the impulse response of the filter G of T or G, okay, which is, you know, is a filtering or in some ways a convolving the data, which is somewhat obvious if you think about that, you know, this U can be a signal, and this signal, you know, can be captured, and this signal can be filtered by a filter, and this linear filter should behave as a conventional way. So if I calculate the autocorrelation of the signal out of the filter, this autocorrelation should contain the autocorrelation of the filter itself. And we will see this concept later. I encourage you to look by yourself and make it with the G1, G2, so on, in order to convince yourself about this property. This property, you know, let me write here the most relevant concept. So the property of G transpose is more general than the autocorrelation of filtering as it contains the truncation effect. Because I truncate the data. Now, if you know, if the word autocorrelation is not clear now, so please remember. Not discussed yet. Okay, we will, you know, we will reconsider everything. Okay, so later on, you know, I mean, engineering is not something that you study this and you forget, okay? So, because if you need to do this kind of job, I mean, you're better to do a different job. So, this means that all the pieces are linked together, okay? So, when there is a time that I discuss about the autocorrelation properties of signals and processes, I will take all this we described now and refresh it, okay? Good. Now we have seen several properties about the linear transformation of Gaussians. No? Now let's make a step forward. I have this. I forgot. A Gaussian dispersion. Okay, it's a very interesting property. The Gaussian dispersion, which I mentioned the other time, is this one. So you remember when I was discussing this, I said. And then I told you these elliptical curves depends on the property. Okay, I did not remember that I had the slides. Okay, ready. Yeah? So now this elliptical property depends on the degree of confidence. And what is the degree of confidence? It means, you know, the probability that I randomly pick up one value that is contained within this convex curve, which is ellipsis. Now let's make it formal and in a multidimensional case. Now, this is called the dispersion. Now, suppose that, you know, I want to calculate, I want to set the probability that the random variable this belongs to a certain convex hull. Convex hull, you know, is a certain area, which is centered into mu x. Okay, so just to exemplify, I mean, of course, what I say is multidimensional. So, but you know, let's say to exemplify, imagine that I have x1 and x2. The mean is here. Mu x1, mu x2, and then, you know, this convex hull is this one. It's the ellipsis, okay? This is the convex hull. So that one is saying, what is the probability that any x randomly pick up? So I take any value. And this belongs into this convex hull. This convex hull is this right here. So it stays inside of that. Stays inside. Now, for a Gaussian case, the probability that, that one stays, in the convex room, and if I fix the probability, let's imagine the probability is 95%, okay? Now, the problem is, can I calculate this convex rule? Can I calculate analytically this one? The answer is yes. I calculate in the following way. So the probability that any x stay in the convex rule is 1 minus the exponential of psi naught squared divided by 2. This psi naught, okay, is related to this quadratic form, which is the argument of the Gaussian. In other words, once I calculate p naught, so assume that I say I want to calculate the convex rule, which is this surface, such that the probability that the value will stay inside is equal to 95%. So what I do, I establish P naught. P naught is equal to 0.95. Then I solve this equation. I get psi. Then I set into the other, and I find the convex rule, okay, the boundary. So let's make, so I fix. So fix P naught, which is the level of confidence. Step number 1. Step number 2, okay. Establish by this one. Establish psi naught squared. Step number 3, okay. Solve for x, the quadratic form. But we know that if I take a quadratic form, which is like hyperparaboloid, and I cut at a certain value, when cutting the hyperparabola, I get the hyperellipsis. Okay. So the output is, when I solve for that, I get this hyperellipsis. Now, sometimes it's important to get the volume of this hyperellipsis. So the volume of this hyperellipsis, once I fix psi, okay, is given by this formula. You don't remember, don't remember by memory. It's a certain formula. This formula depends. Now, this is important. Depends on the determinant of CXX, and depends on another factor. This factor is, the volume of the hypersphere, which unit radius. So this total volume depends on the volume of the hypersphere, which is stretched, okay, which is make it longer, okay, by the corresponding square root of the determinant of the covariance. So the covariance has an impact on the size of this hypersphere. These stretching phenomena. Okay, we will touch that. It's nothing to learn by memory right now. It's only to remember that there is this link. So now one specific formula that we need. You don't understand right now what is the need for this formula, but there is a certain point where we will use this formula as a crazy. Okay? Now, but let me give it in quick fashion. What I want to get is the following. Assuming that I have a joint probability density function that is Gaussian. Let's make it very simple. That is not vector. These are two scalar values. Okay? So imagine that I have x and what's it called, z? Theta. Okay? So my probability density function, is this one, okay? And this is the joint probability density function. So, my goal is the following. This is the joint probability density function. So that is P x theta. Is a scalar, so it's it's adjusting these spaces in two dimensions. My goal is to fix x. So assume that I fix x. This is x equal x0. I want to calculate the conditional PDF. So what is the conditional PDF? Remember, the conditional PDF is the probability of theta, assuming that I is fixed to one value, such that this value is deterministic. It's no more random, okay? So x equal x0. And the way to do is to take this dimension, cut it, and normalize it, and cut it. Okay? So, it is equal to P theta x. I set x equals x0. And then what I did, I normalized it. So I made such that P theta x equal x0 d theta, because this is a normalization factor. Okay? This is what we saw. Such that this area now, which is obtained by cutting, remember, cutting, such that this area now becomes, the corresponding probability density function. So this is the rationale behind, condition. Now, when I take a Gaussian, so a Gaussian is like a bell shape. So when I make a condition, I'm cutting, okay? So beyond the fact that I'm normalizing, I'm cutting. When I'm cutting a bell, I get a bell. Okay? That's what I want to say. So cutting a bell, I get a bell. So that means cutting a jointly Gaussian, arbitrary jointly Gaussian, I get a bell, which means I get a Gaussian as well. Now, let's say, in formulas. Now, in formula means, if I don't have just two dimension, but multi-dimensional way, if I have a joint PDF, which is Gaussian, forget about, the formula, okay? Try to follow the concept. Formula, it's easy once you follow the concept. So if I have a joint Gaussian, okay, then, if I cut it, so what I expect that the output is Gaussian. And then, how do I apply the formula for cutting? So I need to fix x. I don't do explicitly, but I fix x. And then there is a normalization. This comes from the marginalization. Okay? So that is what I get from here. Then when I calculated the ratio, okay, and then from the ratio, then I come out with there's a mistake. There's a mistake. Okay. So that means I marginalize over theta, then I have a PDF of x. Okay, so this is Gaussian, this is Gaussian. Now, this G is a formula. So when I put this formula into there, here and there, now what I get, I need to get the Gaussian, because when I cut the Gaussian, I get the Gaussian. Anyway, now this formula might be complicated or easy, but this formula is a formula that is on theta, and then it's has a certain mean and a certain covariance. So this is the mean. Let's say mean, which is the mean of theta for x equal x naught. And that is the covariance C of theta Okay, when x equals x naught. Which means slice it. Now, don't remember this formula, we will use a lot. Okay? There is a time, approximately 4 weeks, there is a time where, you know, I will go back here and I will say, this example is exactly this. Okay? We will see that, you know, later on, x is the data and theta is the parameters. And our goal will be to estimate the parameters. And then we assume that x and theta will be, you know, jointly Gaussian. Now, when is the time we will discuss it? Let's make a 10 minutes break.